Now, as you might see, this is getting quite technical. So we have a fact here. We have the following fact that 1 divided by 1 minus x is equal to, and this requires some meaning, or in fact, the thing I write over here is going to require some meaning, which I won't get into too much. 1 plus x squared plus x cubed plus dot dot dot, going on forever and ever and ever. So the equality here is in the sense that no matter how close to this you want to get, you can get that close by taking enough terms of this infinite polynomial. Now the infinite, so it goes x to the 4, x to the 5, it goes on forever. It's not really a polynomial, it's what's called a power series. Series is kind of just a fancy word for sum, and they're all powers of x. So for example, suppose you want to get within, let's see, I'll have to kind of reverse engineer this. 0.101 001. Well, okay, look, you can see it's a small, the difference between them is quite small. And if you, so I'm saying that, say at x equal to 0.2, this is equal to 1.25, you can get as close as you want to 1.25. So if you want to get within this many decimal places, you can get there with 5 terms. If you want to get it correct to 100 decimal places, you can do it if you have enough terms. So that's the sense that these are equal. So, yeah. So formally now, okay, so there's different kind of things going on here. So one that people might struggle a little bit is, how can you add up infinitely many things and get something finite? Well, I'll give you a good example, which I'll turn over here to show it. So suppose you have a distance here, let's say 8. And you do 4, so you jump half the distance, then 2, half the distance, then 1, half the distance, then a half, plus a quarter, which would get me something like this, plus an 8, plus a 16th, and I'm getting closer and closer. Now, if I want to get within, say, 1 millionth, I just have to add enough terms. Now, I'm always halving the distance, and so the distance is always getting smaller and smaller and smaller. So this represents 4 plus 2 plus 1 plus a half plus a quarter plus, we kind of said an 8, did we say? So 4, 2, 1, half, quarter, 8, 1, 8, 16, or whatever it is. Whatever it's supposed to represent. So this adds up to 8 in the sense that the distance between, if you keep adding more and more and more, the distance between this sum and 8 gets smaller and smaller and smaller and smaller. Yeah, now the idea is that, so you can write down a technical thing here. So for every epsilon greater than 0, so this is some fancy, this is pure math stuff. So this is as close as you want. Now you can pick any tiny number you want. 0.000, a billion, 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 billion zeros, followed by a 1. There exists a big number n such that the difference between this sum with n terms, so that'll be 1 over 2 to the power of, well, let's see, so this will be n minus 2, I think. And 8 is less than epsilon. So it's basically saying that you can get as close to 8 as you want, right? And here, and oh yeah, the idea is that, like, think about adding up, that's kind of repeating what we just did, but if you do 4 plus 2 plus 1, you can see if you keep going half the distance, you're never going to get bigger than 8, because you're only going half the distance. So that's the, yeah, the thing I was scared about there was that you might think if you add up infinitely many things, you have to get infinity. You don't, if the things get smaller fast enough. Okay, so formally, so let's just write down a formula. Such infinite sums of powers are called power or Taylor series. And I just actually into darts. I only just copped this now. Fill the power Taylor, right? Anyway, so what we have is you have some kind of a formula that's supposed to be, or function that's supposed to be somewhat complicated, and it's equal to some infinite sum. Now it's equal in the sense that we've been talking about. Now, if you are really interested in making that precise, you go and study a pure maths degree. So I would have done a lot of that in my second semester, first year, when I studied maths. So it's sums of powers of x. You can have a constant, as we do here, and then multiples of x, x squared, x cubed, and so on and so on. Now they're usually only valid for some values of x. So we spoke about local approximations. So if these are equal, if you take just some of them, this then becomes an approximation of this. In the same way that, say, if I stop after 1, 2, 3, 4, 5, 6, so the first 6 terms is equal now 7.875. So if you stop early, that the word there is truncate, you have an approximation. And of course we'll be dealing with approximations. We're doing things on computers. Theoretically we have these infinite sums, but on a computer you can only add up finitely many things. Right. In general, power series are valid for only some values. So this is about the local functions, blah blah blah. So there's stuff that's okay. So above, we used a line near x equal to 1 to approximate log of x. We used x equal to 1 because we knew about the function at that point. We knew that log of 1 was equal to 0. As a rule of thumb, we also tend to know all about functions near x equal to 0. And the Mclaren series makes use of this. It's probably worth just commenting, for the case of log, we don't actually know about log of 0 because log of 0 is undefined. It doesn't actually make sense. If you look at what the definition of log is, you'll get a little computer error there, right? So actually, in this context, if you want to do what's called the Mclaren series, the Mclaren just means near x equal to 0. That's all Mclaren means. You would instead look at log of 1 plus x. And then if you take x to be close to 0, 1 plus x will be close to 1. So that's how you do this Mclaren series. So we make some big assumptions that it is equal to what's called its Taylor series. This is a technical assumption. It's not always true, but for us it will be. So you assume that you can write basically this. Yeah. So f of x. Let's maybe just introduce some notation in kit. So I just want to show you a different way of writing this, just in case you see it somewhere else. So this is a sum. So you can do a sigma. And the index is 0, 1, 2, 3. That'll be your I equal to 0. And it goes up to infinity. And every time you're adding up, so A0, A1, A2, A3. So it's AI. And then it's x to the power of I. Now we might just note that x here is x to the power of 1. And x to the 0 is 1, so that's where you get a0. So this is, so assume you can do this. And the problem is to find the infinitely many values of the coefficients. Now this is an infinite number of problems, but sometimes there's nice patterns to these. Okay. So what we basically do is that if these functions are equal, then their derivatives are equal, and this is going to see us on our way. So we'll do an example of this with sine of x. Now we're going to end up with a formula, so we won't have to go through this process that we do every time. But we may as well just see kind of how the differentiation, where the formula comes from. So suppose that sine of x can be written as an, so like this, the crack is that how does it know what sine of 20 degrees is? It uses infinite series, and what it'll do is, if you add enough of these up, the difference between, say, sine of 20 and what they have here is very, very small. So that's how they do it. So what's happening at x equals 0? So these are supposed to be equal for all x. So it's equals for all x, or maybe maybe x close to 0. But actually, I think sine x, this approximation that we come up with is, I think it's valid for all values of x. Okay. So in particular, we're interested in x equal to 0. So if we want these to be equal, they certainly want to have them equal at x equal to 0. So we'll substitute in sine of 0. Now we know what sine of 0 is, but what about, say, sine of 0.1? which, by the way, I probably should say at this point, although my calculator is actually in degrees at the moment, we have to use radians here, and I'll tell you why in a moment. So we're plugging in x equals 0 here. Let's plug in x equals 0 in here. So we get a0 plus a1 times 0 plus a2 times 0 squared. And then I'm going to add in, I'm going to use some notation. Do I do it on the next page? I'm going to write plus this O, stands for order. It's going to be 0 cubed. Now what this means is that everything after this is going to be, so this O 0 cubed, everything is a multiple of 0 cubed. Like say the next one would have a 0 to the 4, that's 0 by 0 cubed, okay? So 0, 0, and then multiples of 0 cubed. I probably should have done one more line, but anyway, so we'll probably use that in a second. So now sine of 0 we know is 0 by looking at the definition, the unit circle, so that's 0. And this is 0 because it's times 0. This is 0. And all of these are multiple of 0 cubed, which is 0. So all these are multiple of 0. So they're all 0. So you're just left with a0 is equal to sine of 0. And sine of 0 is 0. So you're left with a0 is equal to 0. So we have the very first one. Now let's go again. So what we're going to do is we're going to differentiate both sides of this. And then we're going to sub in x equals 0. Okay. So f dashed of x is the derivative of sine of x, which is cos of x. Now that's where we use radians. The derivative of sine of x is cos of x only if you use radians. If you use degrees, the formula is far nastier. Okay, now let's go. Now a0 is a constant. So we differentiate it, we get 0. Fix the constant a1. And the derivative of x with respect to x is 1. Now this should remind you, remember in chapter 2 you're anti-differentiating, so antiderivative say of c1 is c1x. Similar story. Plus fix the a2, what is the derivative, of x squared is 2x. Plus fix the a3, what is the derivative of x cubed? 3x squared. And the rest of them now are, so the next one is x to the 4, its derivative is like 4x cubed. They're all multiples of x cubed. That's what that big O means there. Now what we're going to do is we're going to look at this at x equals 0. Therefore, cos of 0 equal to, now you can get about 0 there, a1 plus, now what happens if I put in x equals 0 here? I get 0, because it's just 0, 2 times 0, and if I put in 0 here, I get 0. If I put in, now these are all multiples of 0 cubed, so everything that's left over, everything is all 0, and what I get here is cos of 0, and cos of 0 we know is equal to 1, and so a1 is equal to 1. And we just keep doing this, and we'll eventually we'll see a pattern. Okay. So repeat the trick again. So now we're going to look at the second derivative. So the first derivative was, and I'll do it up here for space, the first derivative was cos of x. So if we differentiate again, I hope we can see this, maybe let's come here. The second derivative is the derivative of cos of x, which is minus cos of x. No, it's not, it's minus sine. And now let's differentiate the first derivative. So this is a constant a1, that derivative is 0. Fix the 2a2 times the derivative of x, which is 1, plus fix the 3a3 times the derivative of x squared is 2x. And then the multiples of x cubed, when you differentiate them, are all going to be multiples of x squared. And now let's substitute in x equals 0 into this. So we get minus sine of 0 equal to 2a2 times 1 is 2a2. If you substitute x equals 0 into this, you're going to get 0. And if you multiples of 0 squared are 0. And we're subbing in this. And what you get is 2a2 is equal to minus sine of 0. You get 2a2 is equal to 0. And you can divide both sides by 2 or do whatever you want. You're going to find that a2 is equal to 0. If you repeat the trick again, you'll find that a3 is minus 1/6. And with a bit of thought, you can see that the coefficients an are minus 1 to the n. Be careful now. Be very careful. I'm actually not sure. Here we'll gamble it. I think 1 over n factorial. I think that's right. I could actually be wrong. No, that's right. Okay, so what that means is, therefore, sine of x is, yeah, that's right, is equal to, so put in that, so the a0 was 0. Why did that come out as 0? So some of them are 0. Oh yeah, so this is if it's n odd. So this is if n is odd. Sorry, this is very messy. And it's 0 if n is even. So sine of x therefore is equal to x minus x cubed over 6 plus x to the 5. So this minus 1 formula isn't quite correct either. I think it might be, there's some formula here at the end, because it just goes plus minus plus minus. So I'm just going to write alternating here. It's messy, I know. Well, you won't be able to do precisely this, so it's not too bad. This would be 5 factorial minus x to the 7 over 7 factorial plus x to the 9 over 9 factorial, and the pattern keeps on going. Now the factorial is something, so 5 factorial is the same as 5 by 4 by 3 by 2 by 1. Okay, now let's test this out using, now it'll have to be in radians, so I'll have to go into radians 4. So we're going to go with, we'll use this many terms, and we'll do 0.1 of a radian, which is about 6 degrees. So according to this, sine of 0.1 should be approximately 0.1 minus 0.1 cubed over 6 plus 0.1 to the 5 over 120. And you see these numbers on the bottom are getting very, very big. So these numbers are getting very, very small, which has to happen if this is going to work well. Minus 0.1 to the 7 over 7 factorial plus 0.1 to the 9 over 9 factorial. So according to this, it's going with 0.09983341665. Now that's according to the, this is the Mclaren series. And what does the calculator say? Be interested. I don't know how accurate this is going to be. Sine of 0.1, 0.998334165, equal to that many decimal places. So this is how the calculator works. I'm not sure how many it actually uses, because if we did this with 10 radians, you wouldn't get the same thing. I'm fairly sure you wouldn't. But it gives you an idea. So this is how it works. Right? So that's now you know. Now these Taylor series are useful in lots of places in maths. Funnily enough, yeah, we would have studied them in pure maths, but they're actually used more. I don't know, it's not true. They're used a lot in pure maths as well, but they're used in engineering maths, because whenever you've got something complicated, or not complicated, because this is complicated as well, but something that you want to approximate, you'll do this. So if you, like what we've done there is we've chopped off, this approximation is, it's not actually the full Mclaren series. it's the 1, 2, 3, 4, 5. It's 5 terms. We'll call it the 5-term Mclaren Series approximation. Now anyway, you don't have to go through this rigmarole every time. There's a formula for this. Okay, and so if you truncate, that means just chop it off, you can say that f of x approximately is equal to f of 0 plus f dashed of 0 times x plus f double dash, so that means the second derivative evaluated 0 over 2 factorial, which is 2 x squared. Now this is going to be suitably near x equal to 0. And if you move further away from x equals 0, it gets more and more inaccurate. So maybe even if I just do this with maybe the first 3 terms here with 10. So 10 minus 10 cubed over 6 plus 10 to the 5 over 5 factorial. So just using the first 3 at x equal to 10, which is far from 0, is very inaccurate because sign is less than 1. So as you move further away, you have to use more and more terms. And sometimes if you move far away, you can't get it to work. So I know log of 1 plus x, you can only go up to a distance of 1 away from 0. Okay, so we'll do some actual exam questions of these. So this was all the theory.